Hola amigos, now let's see a little bit of this geopotential altitude and geometric altitude relation again, which we have studied earlier. That geometric altitude is this altitude above the surface of the earth, okay, and the change in pressure, infinitesimal change in pressure at a height hg for infinitesimal change in geometric height dhg is given by this formula. And if we take this differential change in pressure dp at the surface of the earth, then we will replace this g over here by g naught, which is inversely proportional to the radius of the earth square. And the value of dh which we will get upon solving this is given by dh and is known as geopotential height. So here we have this geometric height and here we have geopotential height. Okay, so now upon taking a ratio of this and integrating from height 0 to a height h, we have this formula upon substituting g in terms of r square and r plus h g square for geometric height. Okay, so we can see h and hg relation as this. H and hg is same, that is geopotential, and geometric height is same only at the surface of the earth, which is 0. Okay, and everywhere else they will differ by fraction or by small fraction or by very small percentage. Okay, up to 11 kilometer, if you see that the values will only differ by only 1%. So now let's continue with this definition of standard atmosphere, that why we need to define the standard atmosphere or the significance of the standard atmosphere. Because an aircraft has to fly from a hotter region to a colder region, or in a low density altitude to a high density altitude. So for that we need to know at what will be the pressure and density variation. Based upon that, the pilot has to make a decision whether he has to climb a little higher towards a favorable altitude or a little lower to maintain the lift and thrust of the aircraft. And different type of aircraft have different requirements. Like some aircrafts fly very closer to the surface of mountains to prevent radar detections, and some fly very high altitudes like SR-71 to have a reconnaissance to observe any military activity in a prohibited area like that. And so let's observe this. How we generate this is by sending sounding rockets or hot air balloons in the atmosphere, and then taking the average with the height and temperature. Okay, so the y-axis over here is height in kilometers, and x-axis is temperature T with Kelvin. So here temperature is 288.16 Kelvin at sea level or the surface of the earth, and temperature at 11 kilometer is 216.66 Kelvin. And the change in temperature with change in height A is given by minus 6.5 into 10 to the power minus 3 Kelvin per meter. And this change or the slope is also known as gradient. The slope is actually the tangent. If you recall, a slope of xy graph is given by y by x tan theta equals y by x. Similarly, we can define a dt by dh as this. If you compute this 0 and 288.16 and 11 216.66, from this you can calculate the slope. But here is catch, that the slope here you will get, if you compute it this way, will be dh by dt, but we have computed a equals dt by dh. So the slopes m1 into m2, so dh by dt into dt by dh will be equal to -1, which is why a here is equal to minus of 6.5 into 10 to the power minus 3 Kelvin per meter. Okay, so the slope or the gradient dt by dh a1 equals minus 6.5 into 10 to the power minus 3 Kelvin per meter for this gradient. And for this isothermal layer, here the temperature remains constant, okay, with the height from 11 km to 25 km, and 11 km is known as the tropopause. 11 km is generally the height at which aircrafts fly, and from 11 km to 25 it's isothermal because the temperature remains same. And here also we have this gradient. Here is a positive slope, so A2 is positive, which is equal to 3 into 10 to the power minus 3 Kelvin per meter, and it is from 25 km to 47 km. Okay, and at 47 km temperature is 282.66 Kelvin, and till 53 km to 82.66 Kelvin is constant, temperature is constant. And again the temperature varies with height with a rate of A3 equals minus 4.5 into 10 to the power minus 3 Kelvin per meter. So this rate is also known as Lapse rate, which is also represented by lambda equals A, which is dt by dh. So, and the layer is divided into regions like this troposphere from sea level to 14.5 km, and above 14.5 to 47 kilometers it's stratosphere, and above 47 or 48 it's mesosphere, and above that it's mesosphere, and above that is thermosphere. So you can get that from Google or Wikipedia if you want. And like I said earlier, if you know any 2 points, you can form an equation of line from elementary classes. You know that y equals to mx plus c, or y minus y1 equals to m into x minus x1. From that you can form this equation of temperature and height gradient, which is given by t equals t1 plus a into h minus h1. And starting from this gradient layer from the lowermost surface, sea level, so we want to compute the pressure and density ratios, variations actually. If we know pressure at any point P1, okay, and we want to compute pressure at another point, how can we compute? Or we want to compute density at another point, how can we compute? So these are the formulas through which we can compute, and it's given by in terms of ratios, like P by P1 equals T by T1 raised to the power minus G naught by AR. Okay, so G naught is 9.8 and A is lapse rate. Okay, for this it's minus 6.5 into 10 to the power minus 3, and for this it's 3 into 10 to the power minus 3. So please take care of the units. It's in meters over here, but here h is in kilometers, and R is universal gas constant. Okay, 287 and you can compute this now. And rho by rho1 is equal to T by T1 raised to the power minus of whole G naught by AR plus 1. Okay, bracket close. And above the gradient we have isothermal layer. In isothermal layer we have pressure and density ratio equal to each other, which is equal to E raised to the power minus G naught by RT. In the power only, H minus H1 is multiplied by G naught by RT. Okay, thank you. Sorry, one more thing I would like to say, that P by P1 and rho by rho1 is these relations are only valid for the gradient lines, okay, for this and above this, okay, and the graph always remains like this. Therefore, the measurements may vary, but the graph always remains like this. Therefore, it's standard atmospheric graph. And the pressure and density for gradient lines is these equations. Pressure and density calculations are only valid for these gradient lines, and pressure and density calculations for isothermal layer is only valid for these vertical lines. Okay, thank you.